Okay, in this lesson we're going to start the Year 12 work, and the Year 12 work focuses on continuous random variables. So these are variables where the data can take on an infinite amount of values. They often arise from measurements, so for example the time to take for a light bulb to burn out or the height of a tree, because we can measure those to lots and lots of decimal places. So there's a few things that are special with a continuous random variable. So first of all, the function will never be negative. Okay, so it'll always be greater than or equal to 0, just like our probabilities. Okay, that's all it's measuring. If we integrate our continuous random variable, so it'll often be given as a formula, the area under the curve will be 1, because it's like we're summing all the different probabilities. Okay, and they should always add to 1. The peak of our curve will be a maximum, and this will be the mode. It'll be the most popular result. The probability will be the area under the curve. So if you want the probability between, say, 1 and 3, you'll just integrate the function from 1 and 3. So instead of summing the little rectangles in a histogram, we're going to be summing an area under a curve. Now, the interesting thing about a continuous PDF is the probability that it takes on any particular value is 0. Because there's an infinite number of possibilities, any particular value has a probability of 0. Okay, so that is often a little bit weird. So you won't be able to work out the probability of a particular number, just a range of numbers. So once we get into it, you see it is quite simple. So let's have a look at our first example. Okay, we're given a function and it's defined for x being between and inclusive of 1 and 3. Any value of x outside that range will have a probability of 0. So we don't need to worry about that. So in order to be a continuous probability density function, all we've got to show that when we integrate over all the possible values of x, so what I'll do is I'll just go from 1 to 3, because outside of that is impossible. When we integrate the function, we should get 1 because we're summing the probabilities. So we'll go 3x cubed over 3 times 26. So I've added 1 to the power, put the new power on the bottom, from 3 to 1. So this will be 3 cubed on 26 minus 1 cubed on 26. Which will be 26, I've run out of room, which will equal 26 on 26, which will be equal to 1. Therefore, this is a continuous probability density function. Now, we don't really need to show that all the values are less than 1 or greater than 0, but you know that will be, if you think about this, this is a parabola. Something like this, and we're looking at the values from 1 to 3, so you can see all our probabilities will be positive, and since they sum to a value of 1, each individual must be less than 1. So you won't look, let's talk about that later, but I don't think you'll need to explain all that. You'll just need to show it integrates to make 1. Okay, but this graph is very helpful, so I probably should have drawn it here. We can see the mode. The mode will be the highest possible value. So we can have a mode, we just won't be able to have a probability of that occurring. So the mode will be 3. Okay, the probability of 3 occurring is nothing, but it's the one that will occur the most. Don't read too much into it. All right, how do I work out the probability that x is less than 2? Well, I'm going to integrate from the very start, 1, up to 2, okay, because I only want to find the probability from 1 to 2. So this area here that I'm just shading up here. So all I'll do is integrate from 1 to 2. Well, I've already integrated. That was x cubed on 26. So I'll need to do from 2 to 1. 2 cubed minus 1 cubed on 26, being a bit lazy there. What's that? 2, 4, 8, 7 on 26 as my probability. and we'll just leave it as decimals. Alternately, you might be given, between two values. Just be careful if that had a 0, we wouldn't put a 0 here. We always can only put on our limits where we can integrate it. So only values between 1 and 3. But lucky that one started at 1. Now you'll notice it won't matter if it has an equals to or just a less than, because the probability of it equaling to or equaling a value is always 0. So we don't have to worry about this little detail. Okay, so again, I'm going to integrate. I'll show it because I doubt you'll get just 3 of the same in a test. So 1.5 to 1. So 1.5 cubed minus 1 cubed on 26. I will need my calculator for that. And let's pretend the question asks me to go to 3 decimal places. And we'll do our rounding. Did you get 0.091? Okay, another common type of question is they tell you something's a probability density function and they give you pretty much the formula, but it'll have a variable in it. And they'll give you the domain, or they might give you the formula and A might be here. So what we're going to do is we're going to say if we integrate the probability function from 0 to 5, it should equal 1. And once we integrate that, that's ax cubed on 3, we're going to be able to get a formula just involving a. So when we plug in 5 cubed, that's 125. When I plug in 0, that's 0. So now I'll just solve times the 3, divide by the 125. So you'll often have a letter here, or maybe even like a here or here that you'll need to find the value of, but that will be the technique. The integral over the set domain will always equal 1 if it's a probability density function, and then just go from there. Another common type of question is you might be given a uniform continuous distribution function. So this just means everything has the same probability, which is technically none, but let's forget about that. So how would that look? So let's have a look at the example and then we'll come back to this a little bit. A continuous probability function is uniform in the domain 5 to 15. So we're going to do a little sketch of that. So we need to start at 5, go up to 15. These are my x's, and this will be the probability. Now I won't know what that is, but I know it will be uniform. I know it will be the same for everything across there. So a straight line, okay, horizontal there. So how are we going to work out? Sometimes what we often do is we dot here to show that that's the end point. How are we going to work out, we could call that y, how high that is. Well, if this is 10, we know 10 times this must equal 1 because the area under the curve must always equal 1. So surely this has to be 1/10. And this is what this formula is. If you do b minus a, so 15 minus 5, the probability density function will be 1 over that. So that's fairly easy. You'll get used to that. And then just do a quick little check. Does the area of my rectangle equal 1? So in part 1 there, we want the probability of x being greater than or equal to 8. So we're looking from 8 up. So 8's about here. So how far from 8 to 15? Well, that's 7 by 1/10 using the area of a rectangle. I'll go 0.7. What about the probability from 7 to 10? Well, that will be 3 lots of 1/10. And then finally, the probability from 8 to 11. Oh, it would have been good if I had like 8 to 16 up here. That would have been good because remember, we can only ever go up to 15. But 8 to 11, that's also 3 lots of 1/10. And you notice I'm not even caring if it's less than or equal to. That is insignificant in a continuous probability function. But if it's a discrete one, that does make a difference because you're actually counting those particular values. Now, finally, let's talk about the cumulative distribution function. And basically, that's just the integral. So a cumulative distribution function is the integral of the probability distribution function from the start of the interval up to some random value x. So it's basically like integrating, but leaving it in terms of x. Now the CDF this time for cumulative, is continuous. It's always increasing or flat, so it's non-decreasing. The initial value of it must be 0 because the probability at the start is nothing. And the final value of it, if we go all the way to the end of the interval, should be 1 because we've summed up all the probability functions. So it reminds me of cumulative frequency when we did statistics a long time ago. Now the CDF is really handy for medians, quartiles and percentiles. Our percentiles often have special names. The 25th percentile is called the first quartile or the lower quartile, and you would have seen Q1. It's going to keep deleting on me. The 50th percentile is halfway, and you would have seen that as the median. And the 75th percentile, 0.75, is the third quartile or the upper quartile, and you would have seen Q3 in the past. Okay, so this is fairly simple as well. A continuous probability function is given by this, where it goes from 1 to 4. Find the CDF. So to find the CDF, our usual notation is to use a capital Fx, just like a primitive function. And we're going to integrate from the start, which is 1, up to some random x value. So basically we're finding the area of that, but not the whole area, just up to some special value. So let's add 1 to the power and then divide by the new power, so the 4 will cancel, and we'll get x to the 4 and just over 255. Let's plug in x and then plug in 1 and subtract them and neaten it up a bit. We'll have x to the 4 minus 1 over 255. So I have skipped a step there. Feel free to add it in. But combining my fractions, I thought just made it a little bit neater. Now I've got to find the probability that x is less than 3. Well, the long way would be go back here and integrate from 1 to 3. But since I've already found the integral from 1 to any random x, well, I can just plug that 3 in there and do it the easy way. So I'm going to find the CDF, capital F, 3. So I just plug 3 into my cumulative distribution function. Remember, that's finding the area from 1 up to any random point, and I want my random point to be 3. We might go to a decimal, and I got 0.314, but my calculator's a bit dodgy at home, so please check that for me. So again, I'll get you to check on the calculator, and I think I got 0.978, but I'm sure you'll correct me in class if I'm wrong. All right, let's have a look at C now. We're asked to find the median, which means we want to integrate so that our answer becomes 0.5. So we're going to set our cumulative distribution function, our capital F, equal to 0.5. And then I just need to solve that. So I'm going to do 2 steps in one hit to save room. I'm going to go 255 times 0.5. So I'll get rid of the denominator and then add 1. And I get x to the 4 is 128.5. I'll now take the 4th root of that, and I think it's 3.37. Part 2, we're asked to find the 38th percentile. So we want our integration to equal 0.38. So we want our CDF to equal 0.38. Again, times by 255 and add 1, and take the 4th root. Finally, the 7th decile. Remember, deciles mean tenths. So we want 7/10 or 0.7 along the way. So what I'll do, again, I'll set the CDF to 0.7, times by the 255 and add 1, take the 4th root. So as long as you know what to set it to, you can easily solve these problems.